Hello everyone, in this video we're going to be discussing section 4.8, Perform Congruence Transformations. First of all, a transformation is an operation that moves or changes a geometric figure in some way to produce a new figure. So I'm going to have an original figure, and then I'm going to have what is called an image, and that's my new figure. So a transformation can be showed using an error. So if I have my original figure and let's say I want to expand it, I'm going to multiply everything that I have by 2. I'm going to double it in size. So then I go from triangle ABC to triangle PQR, and that then becomes the image. The order of the vertices in the transformation tells you that P is the image of A, Q is the image of B, and R is the image of C. What we're going to be discussing are the 3 main types of transformations. Eventually we will get to a fourth. The fourth one is called a dilation. Alright, so the 3 that we're going to be talking about in this section are a translation, and that's going to move every single point of a figure the same distance in the same direction. So what you can think of for a translation is up, down, or left, right. Up, down, or left, right. We can also use the actual directional words, as in east and west and north and south. Alright, a reflection uses a line of reflection to create a mirror image. So 2 of the lines that we love to use are the x-axis and the y-axis. The x-axis reflection, or reflection over the x-axis, is going to kind of mirror an image upwards or downwards, and a reflection over the y-axis is going to be a reflection left or right. And then we have a rotation, and a rotation turns a figure about a fixed point called the center of rotation. Alright, and it's going to be very helpful to actually draw from the wherever my center of rotation is. It's going to be helpful to draw all of the points, all the vertices of my figure, if this is a square, to my center of rotation. And then let's say I were talking about this one. If I said 90 degrees, I'd map it out, 90-degree rotation, keeping that distance the exact same. And so that right there is my image. Alright, a little bit of drawing can go a long way to help us understand that. So let's look at example 1. Name the type of transformation demonstrated. So here they even draw in a lovely arrow for us, alright, which is allowing us to understand that it is being flipped over the line H. So that's going to be a reflection in a horizontal line, reflection over a horizontal line. Alright, B, you can see the way that this arrow is moving, and you can even see that it is connected to one of the vertices here. So that is a rotation about a point. Part C, it is a nice straight arrow that is simply shifting blue to red, and that is a translation in a straight path. And for the record, my original is always going to be blue in your textbook, and my image is always going to be red. Okay, so let's check out our guided practice. Name the type of transformation shown. So I've got a couple of zebras drinking some water. What would that be? And that is a reflection. Now, if you were thinking about, okay, well, I've got a zebra and then I've got another zebra right here, I feel like I also kind of see a translation, which is always also called a shift. You've got your horizontal and your vertical shifts. Alright, translations. I feel like that's acceptable as well. Alright, Alright, so congruence. Translations, reflections, and rotations, our three types of congruence transformations. When we talk about a dilation, that is another type of transformation. However, it's not a congruence transformation. If you think about the pupil of your eye, when it's dilated, it's getting larger or smaller when it's dilating. So it's actually changing in size. These three, reflections, rotations, and translations, they change the position of the figure, but don't change the size or the actual shape. So a translation. We're going to mess with a couple of examples here with coordinate pairs. So translation is, yet again, moving an object a specific distance up, down, left, right. So you can use coordinate notation to describe the translation. And what we're going to end up doing is utilizing this little, formula. Alright, so x plus a, that's going to be my horizontal shift in the x direction. And then the y plus b is going to be b units vertically up or down. Okay, so if I am to apply, I need to be able to work these examples forwards and backwards. Sometimes I'll give you the translated points, and you'll have to actually tell me what the rule is. Alright, so here, if I have A, and I like to, just write them vertically and then draw my arrows. Alright, B is -2, 4, C is -1, 1, and D is -3, 1. Alright, there's a couple things that I can do. It does say actually sketch out A, B, C, D. Alright, and then apply the transformation. So I need to first figure out what exactly is happening here. So this is going to be right, since it's in the x direction, right 5. This is going to be down 2, since it's negative. So if I were to do the mathematics behind it, I've got -4 plus 5 and 3 minus 2, substituting in all of my xy's that I have, right? Which gives me 1, 1. Alright, and you would do similar operations, alright, for B and for C and for D. Alright, so it's going to end up, here's A, 1, 1, here's B, adding 5, subtracting 2, right 5, down 2. Alright, so we're moving on to reflections now. In this lesson, when a reflection is shown in a coordinate plane, the line of reflection is always going to be the x or y axis, which is fantastic. We love when it's at 0. When we're flipping over another line other than our axes, the mathematics gets a little bit weirder, and so it becomes easier to draw it out, right? Which can be a task if you are not the neatest artist in the world. Okay, so the coordinate notation. If I'm going to reflect over my x-axis, keep in mind that I'm maintaining the distance between the axis. So if I were to pick this point here, and let's call this 5, 1. If I were to reflect it over the x-axis, I know that that's 5, -1, right? Because I'm maintaining this distance. So what happened between those 2 points? Well, x remains the same, but the y's are opposite. So that is why I have my original image, xy, and the image becomes x and the opposite of y. Alright, keep in mind I'm not going to call it -y. I am going to call it the opposite of y, because what if I'm starting below the x-axis? And then in a similar but opposite fashion, reflection over the y-axis, so this would be 1, 1, and this would be -1, 1, right? So the y's are maintaining, but the x's are opposite. So my original point, xy, and my image, if it's a y-axis reflection, is going to be the opposite of xy. I've never memorized these, I've got to be honest with you, but I've always drawn it out, alright, in order to kind of construct these transformations. So, woodworking. You are drawing a pattern for a wooden sign. Use a reflection in the x-axis to show the other half of the pattern. Alright, so it's going to be helpful for me to go ahead and grab some of these points. Right, if I'm going to be reflecting, it just so happens that they have a whole bunch of nice, neat coordinate pairs since they're straight lines there. So I'm going to multiply the y-coordinate of each vertex by -1. Right? It's also fairly easy to draw it out if you've got graphing paper. Alright, so I'm going to list out a couple of points here. I'm going to list out the vertices and connect them. So one was -1, 0. And when I multiplied 0 by -1, I got 0. And then -1, 2 became -1, -2. And so on and so forth. So that became a y-axis reflection. So then I would graph all of these points in, or all of my images, I guess, in addition to the original figures that I already have, the original points, and that's going to maintain the distance. Alright, so looking at guided practice number 2, why don't you guys go ahead and graph it, and pause the video for a second, and a solution will pop up. Alright, so if I'm adding 1 to all the x values and subtracting 1, here is my solution for triangle DEF. Guide practice 3. Okay, rotations. In this lesson, if a rotation is shown on a coordinate plane, the center of rotation is the origin. Alright, we can rotate about a different point, however the origin is a fantastic point to use, 0, 0. Alright, so the direction of the rotation can be either clockwise or counterclockwise, and the angle of rotation is the one formed by the rays, alright, between corresponding parts. So here they're connecting one vertex of the original figure to the corresponding vertex of the image, and those rays, they're saying those rays to the center of rotation create the angle. Now I could use any other points, right? I could use this vertex and this vertex, but you would see that it's still a nice 90-degree angle. Right, so it does say, notice that rotations preserve distances from the center of rotation. So the segments can be drawn to corresponding points on the figures, and those segments are going to be congruent. So that distance right there is going to be congruent to that distance. Alright, so here in example 4, we are going to graph two segments, AB and CD, and tell whether it's a rotation. So we want to actually be drawing in those segments and then give the angle and the direction, so clockwise or counterclockwise. Alright, so when I graph them, I need to make sure to label A, B, C, and D there. So to the origin, I would draw in AO and then CO, and then I would ideally break out my protractor. And just for a bit of confirmation, I would draw in BO and DO as well, confirming that for both of them it is a 90-degree clockwise rotation. Alright, example 4b. As you can see here, if I were to draw these segments for A, B, and C, D, they're not going to maintain that sort of segment rotation that we talked about in the last one. So if I were to look at AC, alright, that distance, you can see that that distance is different. Those segments are not congruent. And then if you were to even look at the angle between AC and, or AO and CO, and then the angle between BO and DO, those are different angles, so it's not a consistent rotation. It's not a rotation. Alright, here in example 5. We are verifying that the translation from triangle ABC to its image, triangle DEF, is a congruence. So we can see that AC is congruent to DF. And we can also figure out that using other pieces of information that we're going to have some other parts congruent as well. You can see that they're already marked. Alright, so keep in mind we've got lots of things in our toolbox. We have the distance formula. That's never going to go away. The distance formula. We have midpoint formula. We've got slope. Alright. Those are things we're going to use for now. Alright, so using the slopes, we know that AB is parallel to DE. So AB is parallel to DE. Alright, and AC is parallel to EF. Alright, if you extend AB and DF, alright, so let's extend AB and DF. Alright, I've now got these beautiful parallel lines. I'm going to draw my triangle on. Alright, what that gives you is a nice line that we can draw here. Alright, which is what they draw. So we know that we've got corresponding angles there. And then similarly, if I were to use those parallel lines that I have created by, finding the slope. So here I've got the slope of the horizontal lines, and if I use this as my transversal now, I know that these angles are congruent. So actually writing out what I have, if I'm extending AB and DE, alright, so here was AB and DE that time, using this as my transversal. I have one set of congruent angles. Extending the other ones, I will end up with that set of congruent angles. So then by the transitive property, I know that those two angles are congruent. So all of that information is going to end up giving me side angle side, but I need one more side, and that I would use the distance formula. So they do break it down. They write 2 radical 2. I'm not sure that we're quite there yet. You guys would get square root of 8, which is the exact answer, and then you would round it. And you would get 2 point something. All of that to say, because triangle ABC is congruent to triangle DEF, the translation is a congruent transformation. Alright, so here's a couple of guided practice. Tell whether triangle PQR is a rotation of triangle STR. If so, give the angle and the direction of the rotation, so clockwise or counterclockwise. Pause the video and a solution will pop up in a second. Alright, so this is a proof. We're not necessarily going to do proofs like this. I am going to ask you on your test what sort of congruence theorems you're going to end up using, and it's going to be important for you guys to list out the information that you have. If you've got a hypotenuse leg that you're using, you want to make sure that you write in there, it is a right triangle, Miss Hlebiczki. Alright, I hope you guys found this video informative. It's not necessary to watch the entire thing. If you guys can skip around to, the different examples, or if you guys can actually read the book by yourselves, kudos to you. Either way, this is one different format that we are trying out. So, best of luck. Good luck, God bless, and good hunting.